Everyone. Okay, so hi everybody. We're happy to have Juan Maldacena today, who will talk about humanly traversable wormholes. So I leave the screen to Juan.
Okay, well, thank you for the invitation. Can you hear me okay?
Yep.
Okay, so we'll be talking about some work that is basically inspired by the paper by Gao, Jeffries, and Wall, and then some follow-up papers that we've been writing on this. And so the outline of this talk is that we'll first remind you about non-traversable wormholes, and then we'll discuss some four-dimensional models of traversable wormholes, including some models, including the possibility of traversable wormholes in the standard model. And then we'll finish with a humanly traversable wormhole in the Randall-Sundrum 2 model. Now, this came out of a motivation, which was to understand better the relationship between quantum mechanics and gravity, and in particular, the relationship between entanglement and space-time connections. And so much of this is connected to this problem of understanding quantum black holes, how the black hole interior is encoded in the exterior, and so on. And in some sense, this whole discussion here will be sort of side development or some application of some of these ideas to this problem of traversable wormholes. But I mean, I will not be talking too much about this relationship between quantum mechanics and gravity, because these constructions can be phrased completely within the language of effective field theory. So more precisely, the effective field theory of general relativity plus quantum fields. And we will take this perspective in this talk, and we'll just phrase everything in that language. And these are curious configurations which are not possible classically and are possible due to quantum mechanics. And they have a non-trivial space-time geometry, a non-trivial space-time topology, and they involve an interesting interplay between different kinds of physics. And for that reason, they are fun. So the first wormhole is just the usual Schwarzschild wormhole. It was noticed that the vacuum solution, so the solution of Einstein's equations in the vacuum, the simplest solution with spherical symmetry is the so-called Schwarzschild black hole, which can be analytically extended to describe a full space-time that has this causal diagram or Penrose diagram, which contains two separate exteriors joined through an interior. And so this is a solution with no matter, and describes a wormhole. So this spatial geometry at t equal to 0 describes a three-dimensional space that connects to a second three-dimensional space, asymptotically three-dimensional flat space here at infinity. And so we can think of this as two black holes sharing a single interior. There is a very closely related geometry where we put these two black holes in the same space-time but at very long distances. And so you would see from the outside two separate black holes, but they are secretly connected through the interior. So they share the single interior. Now, these wormholes are not traversable. So if you send the signal from the right side towards the left side, the signal will come along this direction. So the fastest it can travel is the speed of light, which is a 45-degree line in this diagram. And it ends up that the singularity cannot go to the other side. But an interesting point is that it is almost traversable. It's pretty close. So you can send the signal very close to the horizon. And the signal does not make it, but it looks like it almost makes it. And you might wonder whether perhaps some perturbations of this metric will make it traversable. And it turns out that in classical general relativity cannot be made traversable due to the integrated null energy condition. Now let me remind you about which the integrated null energy condition is an energy condition which is true in classical physics. Now then we can come to quantum mechanics, and In quantum mechanics, you can have regions where, so the null energy condition is a condition on T++. It's roughly is the energy density divided by the energy density minus the momentum density should be positive. That's essentially what it is saying. And we can have regions where that is negative. And it's not easy. It's simple in even in free field theory to see that you can do this. And it turns out that even the integrated null energy condition, so when you integrate along a null line, or it could be a null geodesic, even that one can be violated in some cases. So in flat space, this is, if we were in flat space and we take a null ray in flat space, this has recently been proven by various groups to be definitely positive even in interacting theories. But when you have a non-trivial topology, it might sometimes be negative. An example is a cylinder. So if you have a two-dimensional cylinder and you take a light ray gamma, which goes around the cylinder. So by a 2D cylinder, what we mean is a 1+1 dimensional theory where space is a cylinder. Space is a circle, sorry. Space is a circle, and then time is the vertical direction, let's say, of the cylinder. And in that situation, we know that the T++ is essentially the energy and receives a negative contribution from the Casimir energy. It's the same as what's called L0, if you're familiar with that. What that means, if not, doesn't matter. So it can receive a negative contribution, and then when you integrate, it's constant, and when you integrate it around the circle, you still get the negative contribution because it's just constant. Now, the true quantum condition, so a condition that is believed to be true and it's proven in some cases, but not in all, not in the most general case, but the condition that is believed to be true is the achronal average null energy condition. And this applies to the fastest null ray. So the idea is that if gamma is not any null ray, but the fastest null ray you can have in your spacetime, and with that, so this is just an informal way to say it, the achronal condition means that 2 points along this null ray are not time separated. So in the case that the null ray goes around the cylinder, when let's say we go, for example, once around the cylinder, we get to 2 points that are separated by a time-like distance. And so that line is not achronal. And so that's okay. So then this can be violated, can be negative. But if it was achronal, then it should be positive. So that's, and this achronal average null energy condition forbids the science fiction wormhole. What is a science fiction wormhole? It's usually a plot device that is used to travel faster than the speed of light. So question is, do the laws of physics allow faster than light travel? And the answer is no, because of the achronal average null energy condition. And here, I think when we talk about the laws of physics, we talk about very general principles, like general relativity coupled to quantum field theory. We're not talking about the particular matter theory that we have in nature, but any possible matter theory that obeys the principles of special relativity, quantum mechanics, and then coupled to general relativity.
Juan, can I ask a question?
Yeah, please.
Are there achronal light rays on the cylinder?
Yeah, no, not that are infinitely long. No, there aren't.
So in that case, what would be the content of the achronal average null energy condition?
Yeah, it just doesn't put any condition because there is no. There is no light ray. There is probably some condition that says that the energy could not be too negative, but I don't know exactly what it is. So, of course, for conformal field theories, we know what the answer is. It's the negative energy cannot be bigger than -2/24. Well, yeah, but there's probably also some condition in general. Yeah, please ask questions during the talk. Now, those conditions forbid sort of shortcuts, so faster than light travel, but what about sort of longer detours? So could there be a wormhole where the observer going through the wormhole, so in this case, for example, we could go outside the wormhole, and the wormholes are separated by some distance d, so it takes some time of order d going outside, and it could be that going inside might take a time which is bigger than d. So is that allowed or not? And in order to have this type of configuration where light rays sort of that go in get focused and then defocused, you necessarily have to have some negative null energy in this region near the bottom. So these configurations are definitely forbidden by classical physics, but you could wonder whether quantum physics might allow them. And the answer, of course, will be that it will be allowed, but you will have to include some quantum effects. And so this talk will be about these wormholes. So there will be traversable. They have no horizon, so they are not black holes. They also do not allow faster than light travel. So if you're a science fiction fan, this might seem bad, but if you like the principles of physics, of causality, and the principle that there is a maximum speed of propagation of signals, then that's a good thing. So a side point is that when we talked about the travel time, we are talking about the travel time as seen from someone who remains outside. So if you send a signal into this mouth, the signal will come out of this mouth at some time t, which is bigger than d. However, the proper time for an observer that goes down the wormhole might be much shorter, because the observer gets accelerated at high speeds. There is a high redshift factor here, and so it might be much shorter, and indeed we'll see that it is much shorter. Now, the constructions that we will discuss require some special matter, but still matter that obeys the rules of quantum field theory. So it's not exotic in the sense of violating the achronal average null energy condition. So it's consistent with the rules of quantum field theory.
Yep. Sorry, there is a question by Nick Warner.
Yeah, sorry, Juan, a stupid question. How do you distinguish the wormhole picture from just having a compact universe where you take the long way round the geodesic? Say you've got a cylinder and you're a meter apart on one way, but you can go around the cylinder the other way 100 meters apart. How do you distinguish the wormhole from that?
I would like to distinguish them by saying that they're embedded in some asymptotically flat space. Yeah, it's true that in a cylinder you have a similar effect, but for the case of a cylinder, you don't need any quantum effect or anything like this to have that compact circle.
Yeah, but that was kind of my point. How do you know whether you need a quantum effect or not? If you've just got some compact spatial manifold, you can go the pretty way as well as go the short way.
Yeah, so this arguments that you cannot have topology and so on, they rely on having an asymptotically flat space or asymptotically ADS space, for example. So this average achronal average null energy conditions is for light rays that are inextendable. So complete light rays that go from plus to minus infinity. I think I'm not answering. I think they're slightly different in spirit, in the sense that we have some, in this case, we have some asymptotically flat space which defines a kind of background causal structure. And then we deform locally the geometry by one of these wormholes, and we are wondering whether after we do this deformation, we will alter or not the causal structure of the background space-time. Is that the...
I think the asymptotic flatness deals with the problem I was wondering about, but I'll think more. Okay.
Yes.
No, that's kind of the question.
I mean, I should emphasize that. Sorry. Yeah, please.
No, in 4 dimensions, there are some theorems called chronology protection theorems, which, for example, prohibit black rings in 4 dimensions. Essentially, any geodesic going through the space has to be deformable into a geodesic at infinity. I'm just wondering what's making these spacetimes avoid this theorem.
Yeah. Indeed, there are such theorems, yeah, I guess I was referring to those theorems here, and they forbid a non-trivial space-time topology like a one cycle like we have here, and those theorems rely on the average null energy condition.
Oh, okay, with Anek, okay.
Yeah.
And you can avoid them using this integrated null.
Yeah. If this line, they're avoided because quantum effects can allow a violation of the average null energy condition, but not a violation of the achronal average null energy condition. So we still preserve causality.
Mm-hmm. Okay.
So
Maybe another question: can you do black rings in 4 dimensions using these things then? Just as a side, maybe in the future.
Black rings in I don't know.
But they are forbidden, but again, because of the same thing. So maybe one can actually realize them using this trick.
Yeah, I don't see. Yeah, it might be, yes.
Okay, anyway, just thanks.
Sure. Okay, so the simplest example of a theory that allows these kinds of wormholes is a theory that it's, let's say, in flat space, so zero cosmological constant, and we have an Einstein term and a Maxwell term, so U1 gauge field, and then a massless fermion that is charged under the U1 gauge field. This could be the standard model at very short distances where the fermions become effectively massless. So we go to distances much smaller than the Compton wavelength of the fermions. And then the U1 that appears here could be the hypercharge, the U1 of the standard model. So the first starting point is to consider near extremal black holes. So we have the black hole geometry of a charged black hole, of a magnetically charged black hole. So we're going to imagine there is a black hole which carries magnetic charge Q, and we go near the extremal limit where the mass is very close to Q. And in that limit, there is the geometry develops a very long neck. So with the geometry of AdS2 times S2. You can also picture this as a big gravitational potential well. There's a big redshift factor between an observer sitting still here and an observer at infinity. And the near extremal geometry will then, this will be capped off by a horizon that is at a position which gets deeper and deeper as the temperature becomes smaller and smaller, and as we approach closer and closer to extremality. Now we consider, let's say, 2 extremal black holes where these necks are infinitely long, and we bring them close to each other, and we imagine that one is positively charged and the other one is negatively charged. And now these throats, we connect them to each other. I'll explain that what we mean in a second. So we connect these 2 throats to each other. And this connecting them requires only a small deformation of the geometry. And there is one free parameter at this stage. So when we connect them, we can connect them deeper and deeper inside this very long throat. And that's a free parameter that we have in this ansatz. So far, this is an ansatz for the geometry. The fact that this is a solution to Einstein's equations will come later. So now here we'll explain a little better what it means to connect the 2. So first, this green rectangle is the Penrose diagram of full AdS2 space, so a constant 2-dimensional space with negative curvature. And we said that locally the geometry was AdS2, so if we just write global AdS2, this is its Penrose diagram here. Now, when we have a near extremal geometry, what we have is really the region outside the horizon is one of these triangles, one of these causal wedges. You can view it as a Rindler causal wedge inside AdS2. And when that near horizon region of that throat region is joined to flat space, then we are cutting off this black region of AdS2 and replacing that black region by 4-dimensional geometry. So here in the central part, we have AdS2 times S2. And then in this black part, this opens up, the S2 opens up and connects to flat space. And here the full red and black regions, they together will define the near, well, this, especially the red regions, is the near horizon geometry of 2 copies, or the full sort of Schwarzschild-like solution, but for Reisner Nostrom black holes, for charged black holes. Now, in this case, the fact that we connect to flat space costs some energy, which is of order of the difference in mass between the extremal mass and the non-extremal mass, and that is proportional to the temperature squared, or inversely proportional to the square of beta, where beta is the inverse temperature, and is roughly related to the redshift factor difference between the very near horizon region, so some region of order 1 radius of ADS from the horizon, and infinity. Okay, so that's one thing we could do, but another thing we could do is we could start with this diagram and connect to flat space in such a way that we preserve the global time translation symmetry. So here, when we connect this to flat space, we preserve the sort of, you could call it the rendered time translation symmetry, or Schwarzschild time translation symmetry. Here we could preserve the global time translation symmetry. And so this locally, the connection to flat space is the same as the one we had here, but the global space-time geometry is different in this case. So in this case, we have no horizon, and we have time translation symmetry. And this whole green region is representing the this region that goes, let's say, between this circle all around the wormhole to this other circle, let's say. Again, here we can define something similar to a length of this wormhole, which is again given by the redshift factor between the center and infinity. And the energy of this configuration, again, will be given by, at least the gravitational contribution to the energy will be given by a similar formula, where instead of beta, we have this length of the wormhole defined the way we just mentioned. So for now, we have just an ansatz for the geometry, and now we'll consider the fermions propagating in that ansatz. Now, we had one 4-dimensional massless fermions, and this gives rise to actually a set of Q 2-dimensional massless fermions that propagate along the magnetic field lines, where here this little q is the magnetic charge of the configuration viewed as an integer. So the magnetic flux is quantized, and so q is the amount of magnetic flux that we have. We're imagining the fermion has charge 1. Of course, you could do fermions with different amount of charges. And so what happens here is that in the presence of a magnetic field, the fermions give rise to a set of Landau levels. And for fermions, there is actually a zero energy Landau level. So we're used to the fact that for bosons, there is a non-zero Landau orbital Landau energy even for the lowest level. But for a fermion, the coupling to the magnetic moment can completely cancel that and gives rise to a zero Landau level. There's also an argument based on thinking about anomalies that of chiral anomalies of 4-dimensional fermions that should descend to 2-dimensional chiral anomalies that ensures that this should happen. But it's easy to compute by just writing down the Dirac equation in the presence of a constant magnetic field. So once you have this Landau level, so the lowest Landau level is a little orbit, you can view it as a little orbital that is located around with an extent proportional to the flux, to 1 unit of magnetic flux. And then these fermions would, in the directions orthogonal, but in directions along the magnetic field, they would follow the magnetic field lines, very much like we have for charged particles moving in the magnetic field of the Earth. Of course, if you have a big circle, that's a highly excited Landau level. So the smallest possible circle size, that's the lowest Landau level. So when we then look at this, we have these fermions that move along. Before we talk about the fermions, let's discuss the magnetic field lines. So we have a positively charged object and a negatively charged object. The magnetic field lines go out of one and into the other, and inside the wormhole they just connect. And so there are magnetic field lines that follow a line of a follow a closed circle. And so if we had these fermions can, in principle, propagate along these magnetic field lines. And an interesting point that is important for making the construction controllable is that just a single field gives rise to Q two-dimensional fields. And so there's a relatively large enhancement of the number of massless fields and of the quantum effects or the quantum ground state energy of these fermions. So when these fermions move along these magnetic field lines, when these fermions exist along these magnetic field lines, even if they are in the ground state, they give rise to a negative Casimir energy, which is of order minus Q over L. So this is the ground state energy of fermions on a cylinder. We said we define this parameter L as could be a quotient of redshift factors, or we could define it as being related to the time it takes for a signal to go in and come out as seen from the outside. So these turn out to be equivalent definitions by using the shape of the geometry that we discussed so far. And that's so far a free parameter. And we imagine we put these two objects at a distance which is, let's say, comparable or smaller than L. And in this situation, then the Casimir energy will be Q over L. If this distance is comparable to L, you have to take into account that the total length is L plus D, and so you can write something similar and you get similar physics. But we won't discuss that case too much. Okay. Now we take this negative energy that we got and we can put it in Einstein's equations, and then we can find the solution with this wormhole shape. So we find the actual value of L that determines this. And one way to conceptually understand how to fix this value of L, actually this way is not just conceptual, but it actually, you get the precise numerical coefficients from this argument, though I haven't put them in here, is to view this as a balance between the gravitational energy that it costs to deform this wormhole geometry to put. So this is the energy that is required to connect the wormhole to flat space. And then this is the negative energy of the fermions. And then we choose an L which minimizes this energy, and this determines the value of L. So value of L is increases with Q, and is Q times the radius, the extremal radius. So the extremal radius is the typical size of the wormhole throats, is the size of the S2 in this extremal black hole solution. So for large charges, this is a distance much bigger than the size of the object. And this balance and, well, these Einstein's equations we're talking about are the Einstein's equations in the wormhole region. We still haven't solved the Einstein equations outside. And in fact, if we had this configuration, these two black holes will attract each other and fall into each other. And one way to prevent that is to make them orbit around each other. And if they can be far enough that the effects of them orbiting each other are not very important, so that they orbit slowly compared to the time L that we discussed so far. And this then gives a long-lived state. So it doesn't live forever because it will slowly decay by emitting electromagnetic and gravitational radiation. Also, these magnetic black holes in principle could decay by emitting monopoles, but that's magnetic monopoles, but that's exponentially suppressed for large Q. But well, that's another possible reason they could decay.
Question.
We have a question from Panos Bexios.
Hi, Juan. So do you have an estimate how long-lived it is based on these parameters?
Yes, you can estimate. It depends on the distance, but yeah, you get the estimate by calculating the rate of emission of electromagnetic radiation. That's the dominant effect. It's bigger than the rate of emitting gravitational radiation. It's some power of these parameters. It's in our paper, but I don't remember it right now.
Okay, thanks.
Mm-hmm. The important point is that you can make it larger than L. the lifetime to be larger, much larger than L, parametrically larger. So in this regime, there is one parameter which is Q, and you can, if by making Q large, you can separate all the scales from each other. So there is a scale which is proportional to Q, which is this RE. So RE is L Planck times Q. I should have emphasized that the only dimensionful scale is L Planck. And then there is this length L, which is Q times that. And then we can choose a distance so that this lifetime is much, much bigger than L.
So, question, Juan, is it crucial that the black holes don't live in disjoint universes?
Yes, yes, it's crucial for, yes, well, it is crucial that there is that these fermions can go from one to the other, forming a closed loop of finite size, right? Now, another construction you could imagine is to have, for example, two ADS4 spacetimes with one black hole in each, but that these two ADS4 spacetimes have some boundary conditions where the matter fermions that live in ADS4 can move from one to the other. So that would also be possible.
So why is this required?
Well, here it was required to give rise to this negative Casimir energy. So if they live in disjoint universes, they wouldn't give rise to this negative energy.
I see.
Put it another way, if you...
Oh, let me put it in a different way, so perhaps will be more clear. So let's imagine that here we put a boundary condition, a reflecting boundary condition here, right? That completely disconnects the two universes. Then instead of the fermions living on a circle of length EL, they would live on a strip of length L, okay?
Yes.
And the Casimir energy will be less, I think there are some factors of 2, would be a less negative Casimir energy. And that less negative, that's if the fermions were in flat space. But here there is also a contribution from the conformal anomaly, which because ADS2 it's conformally flat, but not flat. And when you take into account that contribution, it precisely cancels the energy of a fermion with Dirichlet boundary that lives on a strip. So if we had a strip of length L, this conformal anomaly piece would exactly cancel that negative energy to give a 0 energy for such fermions.
I see. Thanks.
The reason you get 0 energy is also perhaps easier to understand from symmetry principles. So if you have a massless field living in ADS2 with Dirichlet boundary conditions on the two ADS2 boundaries, that's a configuration that preserves the full ADS isometries or SL2 symmetries. And this negative energy we're talking about violates that symmetry. So this you cannot have a T++ component consistent with the ADS2 isometries. The ADS2 isometries are violated in our case by the fact that, so if you look at this diagram, if you say that the fermion at this point can interact with the fermion at this point, or put such a boundary condition, then you are violating some of the ADS isometries, because there are some isometries that move this point forwards in time and this point backwards in time, like, for example, this booster on the center. Is that more clear now?
Thanks. Thanks.
Any other question? Now, usually a question is whether, let me ask a question that wasn't asked yet, but maybe let's address this point now. Normally, people have a, well, if someone comes and tells you that there is some solution that they found that balances a classical effect against a quantum effect, as we're doing here, you might be suspicious, because the classical effect is bigger, and then you have a small quantum effect. What makes sure that higher order quantum effects are not important at the same time? That's a very legitimate concern. And the reason this is working here is that the classical effect is sort of anomalously small. So it's very small because of the fact that you can stretch this wormhole, you can make it larger. And you see here that this classical effect becomes small as L becomes larger. It becomes smaller faster than the quantum correction. And so it's basically this effect that manages to give a controllable expansion. So you have a very small classical term, and then you can balance it against the quantum term, and then higher order terms are then under control. Okay.
Yes, there's another question by Emil Martinez.
Yeah.
Yeah, so somebody sitting in the outside region outside these throats, what do they see as the ADM mass of this object?
Yeah, I think it should be smaller. So it should be smaller than the extremal mass. Should be below the extremal mass by an amount which is of order Q over L. So after you after you put in this, so let me be more precise. So by extremizing over L, you get some minimal energy here. So this energy here is the mass minus the charge, right? So it's the deviation away from extremality. And that quantity at the minimum is negative and of the order of either of these two terms. So of order, let's say minus Q over L, and that is of order 1 over RE, okay? So in this particular case, so it's a very small energy in this setup. It's an energy of order 1 over the Schwarzschild radius. So that's the energy of a quantum with the size of the black hole.
Yes, Anos has another question. Then we can probably move on to the rest of the.
So, doesn't that mean that if you're the human that's trying to go through this thing,
yes,
is there a large blue shift between the top of the throat and the bottom?
Yes, there is a large blue shift. We'll discuss that in a second, because these black holes are not good for a human, the ones you would get with this procedure, because the binding energy is 1 over RE, right? This is 1 over the size of the black hole. If you have a person sitting near this black hole, it has an energy much bigger than that.
Right.
So if you throw in such a person in these black holes, it would create a non-extremal black hole.
Right.
Even if you started with this wormhole, it will create a non-extremal black hole. So these wormholes that we are discussing so far, just with this single fermion and so on, will allow you only to send signals whose wavelength is bigger than the size of the black hole.
Mm-hmm.
So Juan, just to clarify, you just said that this thing has an energy which is comparable with the energy of a single Hawking quantum, didn't you? You just said it's about one.
Well, it's not Hawking. It's because the temperature might. Well,
it's zero. I know, but
it's an energy of order 1 over the size. Yeah, that's what I said for this case. Yes, that's an important point. Yeah, maybe I should add this format.
Doesn't bother you in terms of the quantum properties of this object? That it's got an energy of scale, the Compton wavelength of the object itself. That's
no. It's not the Compton wavelength of the object. So because the object is very massive, right? It's just the order of 1 over the size of the object.
Okay.
Right.
Okay. Yeah.
So this has a geometry which is very long, and has this type of energy. So. Of course, yeah, if you send in a wave that has a wavelength much bigger than 1 over RE, then it can go in, it gets blue shifted to wavelength which might be smaller than RE at the bottom of the throat, and then come out on the other side as, again, a very long wavelength object. In usual discussion of near extremal black holes, similar things happen, right? For example, in the geometries that you were considering, these fast balls with caps at the very bottom and so on, you have this very large redshift factor. So if you wanted to explore the bottom of such a throat, you have to send in very long wavelength excitations from the outside, so that when they get to the bottom of the throat, they have a wavelength comparable to the features that you want to see.
Yep.
Right?
Yep.
Yep. Okay, so I wanted to emphasize that, well, in this case, the time that it takes to go through the wormhole, from the point of view of an observer that remains outside, is L, as we repeated many times. But as seen from someone who's traveling through the wormhole, it is of order RE. And the reason is that the process of going through the wormhole is similar to just one oscillation in this ADS2 geometry. And the proper time for one oscillation inside ADS2 is, I mean, a particle which is in ADS2 could be sitting straight in the middle of ADS2, or it could be oscillating. And both of them, well, in one oscillation, you see a time which is of order RE, maybe some factor of pi, but of order RE. And this could be much shorter than L. Now, in the standard model, we could have such wormholes from magnetically charged black holes. They are very small, and they are also at very short. The black holes themselves are very small, but also you have to put them at distances smaller than at least the Compton wavelength of the electron, so that at least the electron would be effectively massless. There are further effects in the case of the black holes in the standard model, which is the formation of a certain electroweak corona and so on, which I won't discuss in detail, but kind of fun to think about magnetic black holes in the standard model. And if you wanted to make them larger, then you couldn't apply this mechanism to produce the wormholes, because the masses of the fermions would suppress exponentially the Casimir energy, and you wouldn't be able to stabilize them. Now, we've only have argued that these are possible long-lived solutions. At least I personally don't know any simple way of producing these configurations if they were not initially present. I think in principle, if we held two nearly extremal magnetic black holes in place and put them close to each other, then we would expect that eventually perhaps the wormhole should form, because it's a lower energy configuration, as we were saying, has less energy than the extremal energy. But it could take an exponentially long time, and at least I don't know a way to construct them in a relatively short time. As a side comment, there is a closely related configuration in the SYK model, and those can form rapidly, but that rapid process seems to depend on some of the SYK details. So I don't know how to generalize that for the near extremal black holes. Now, the question is, so we just seen that these wormholes are very fragile, in the sense that at least with one massless fermion, we got that the binding energy was essentially 1 over the size of the object, of one of the extremal size. So this type of object would never be useful for sending a particle which is smaller than the black hole. But you can enhance the effects of these traversability effects, and you can make that binding energy bigger by putting not just one fermion, but many fermions, okay? So even in the original U1 gauge field model, you could imagine having a large number of massless for the fermions, and then this can make this can certainly increase the size of the binding energy, make the wormhole more traversable, and allow you to send through the wormhole objects that are smaller than the size of the black hole, okay? So that feature that we were discussing a moment ago is a feature present for just this case of one fermion. But if we increase the number of fermions, then you can make it, you can make the binding energy bigger and be able, in principle, to send something smaller. And so we, of course, in nature, we have some fixed number of fermions, but maybe if you say, okay, maybe there's some dark sector that can lead to more fermions, or you just could postulate a theory where you have more massless fermions just for fun, and see what happens. So possibility is to have this same model of a dark U1 gauge field with a bunch of massless fermions, and you get formulas similar to the one we discussed before, with the number of massless for the fermions multiplying various quantities. And the net effect is to make the wormhole easier to traverse and less fragile. However, if you set for yourself a goal, which is to make it humanly traversable. So let's say we postulate a dark sector which is such that at least it agrees, so it's unexcited, so and it agrees with what we have so far in nature. Then you cannot make a humanly traversable wormhole with this type of setup. What happens is that in this case, the number of fermions you need to put is so big that the U1 gauge field gets strongly coupled, so you can't analyze it. So that makes you think that perhaps if you have a dark U1 gauge field plus a conformal field theory with a U1 symmetry, but that maybe it's strongly coupled, then you could perhaps do that. Now, let's discuss what it would take to make a humanly traversable wormhole. So the first condition is that it should be large enough that we are not killed by tidal forces. So I mean, your first naive idea is that the RE should be bigger than the size of a person, so bigger than a few meters. But that's not enough. So you actually need that there will be some tidal forces in such a configuration, which are proportional to the curvature, which goes like 1 over RE squared, and are of course proportional to these tidal accelerations between your head and your feet, proportional to the size of the person. And if you limit them to be, let's say, what the people say you can sustain without dying, then that gives that RE should be bigger than roughly the size of the Earth. So that's the smallest wormhole you could hope to traverse. By the way, this little calculation is the same calculation that tells you that in order to be able to cross the horizon of a black hole, you need to fall into a black hole which is also bigger than this size. Okay, so you could fall into a black hole which is a supermassive black hole of the size of the solar system, like the one in M87, whose picture was taken by the Event Horizon Telescope. So such a black hole has a much bigger size than this, and so there you could fall into that black hole and survive crossing the horizon and live for a while inside that black hole. But you couldn't do that for a stellar mass black hole, which has sizes of order 1 kilometer. Okay, so we want a 4D theory that we can couple to a magnetic field, and is such that when we put the theory in a magnetic field, it gives rise to an effectively 2D theory, similar to what we had for the fermions in the lowest Landau level, and that 2D theory has large central charge. And one such example is to consider a holographic 4D theory, so a theory that is described by an ADS5 gravity theory, and in ADS5 it contains 4D gravity plus a 5D gravity plus a 5D gauge field. Then if we put a boundary condition corresponding to a magnetic field on the boundary of ADS5, then we can see that such a setup leads to a flow from an ADS5 geometry to an ADS3 times R2 geometry, or depending, maybe if you had S2 here, it would be ADS3 times S2, which is signaling the appearance of a two-dimensional CFT, similar to what we discussed before for the fermions. And so you can solve the equations. In this case, I'm not telling you what the solution is, but it's a fairly straightforward exercise to solve this, find this flow. And the effective 2D, you can compute the effective 2D central charge in terms of the properties of the 5D theory. Okay, so we can embed this as a type of Randall-Sundrum 2 model where, so Randall-Sundrum 2 is a model where you have an infinite extra dimension and a Planck brane. So the idea is we live here on this Planck brane and the extra dimension extends towards the infrared. So this it's a geometric construction of a 5-dimensional theory, which has the same physics as 4D gravity plus a 4D QFT with a scaling symmetry, or a CFT. And we consider this to be an extra dark sector, right? So this is the more precise metric. And in addition, we add this bulk U1 gauge field. And again, as we said, it leads to the 2D massless modes. And for our purposes, what we want to do is to maximize the two-dimensional central charge. So that is maximizing the radius of, and that turns out to mean that we want to maximize the radius of the 5th dimension. And the current limit on the radius of the 5th dimension is that it should be bigger than about 50 microns. And so taking this value and the previous minimum value for RE, that is what is necessary to allow for a person, we get that the smallest value of L is about 10,000 years.
Sorry, Juan,
Yeah.
by the radius of the fifth dimension, you mean the ADS scale, right?
Yeah, the ADS radius, yeah. Okay. So then the final solution we discussing is a solution where the geometry and the topology, mostly the topology is as written here. So the Planck brane somehow has this extra wormhole, and the wormhole is filled in the fifth dimension in the same way that it would be filled in as if we had borrowed a little hole into the fifth dimension, okay? So in this case, if we view the Planck brane as the surface of the soil and then as the rest of the soil, this is literally a hole that the worm would make going between two mouths, right, in the soil, except that the hole is made into this five-dimensional geometry. If you take one of these magnetic flux lines and you fill it in the fifth dimension, so near the Planck brane, you have some ADS5 geometry, but as you go deeper inside, you have an ADS3 times S2 geometry, and the geometry of this full space, well, has time, and then the spatial circle is this circle of the magnetic flux line inside the wormhole, and a piece of the magnetic flux line outside the wormhole, and then it's filled in the interior as it would be filled in ADS3. So that's basically the geometry we're talking about. Now, one interesting point is that from the 4D point of view, the Casimir energy was a quantum effect. However, from the five-dimensional point of view, it's a classical effect, and it comes from the energy of the gravitational energy of the ADS3 times S2 region of the geometry. So it comes from the fact that when we look at ADS3, this is in global coordinates, the energy of this ADS3 space is minus, let's say, C over 24 and so on for the left and the right movers. Now, in 5 dimensions, this classical topological censorship theorem should apply in the sense that we shouldn't have a non-trivial pi1 for the light-like geodesics. And indeed it does. So if we think about this light ray that goes through the wormhole, that light ray can be continuously deformed to a light ray that stays outside the wormhole by moving it in the 5th dimension. Okay, it's okay. Now, as a fun science fiction application, we can say that we could use these wormholes for future ecological galactic travel. So you could travel to a distance of about 10,000 light years away, and you fall in, and the time it takes for you to travel, if you are traveling here, would be it would be less than a second, because RE, it's less than a second. And so, and in addition, you don't need any fuel to accelerate and decelerate. So you could of course travel in 1 second proper time if you accelerate very fast and then decelerate very fast on the other side. But here, the gravity does the work for you, and you don't need to do that. So that's a science fiction application. Now, of course, this has lots of fine print. I would certainly not saying, well, let me be very clear. Of course, I'm not saying, you probably all understand that I'm not saying that these wormholes are present in nature. Our universe is probably not described by this Randall Sundrum 2 model. Any object that is falling into this wormhole from the other side would be highly boosted when it meets the traveler here at the bottom. In fact, for these parameters, the boost factor here at the bottom is 10 to the 12. So even just the cosmic microwave background entering on one side is enough to kill the traveler. There is no simple mechanism for producing the wormhole in the first place. And finally, another issue is that in order for this wormhole to exist, you really need that the dark sector should be cooler than 1 over L. So the temperature of the dark sector should be smaller than 1 over L. And L, is this distance. So this is a incredibly small temperature. And indeed, even if you were able to produce it after the Big Bang at this very tiny temperature, even the gravitational soft modes that are emitted from stars that Weinberg computed, or the 5-dimensional version of what he computed, that's enough to heat the dark sector to a higher temperature. Okay, so these are some practical issues, but so you should view this as a fun set of parameters to understand and at least see how you could view this as situation, or you could say, well, they are not possible for in any practical sense.
There's one question.
Yeah, please.
Yeah, so I guess I would add a number 6. So
yeah, please.
Yeah, so if I fall into this thing, by the time I get down to the bottom, I'm traveling pretty fast.
Yeah, yeah.
So aren't the curvature effects magnified by the blue shift?
Well, in principle, yes. So for a generic curve space, but here it's important that the space is ADS2. So
But it has it must have some small multiple moments that are deviations from ADS2.
Yes, that's true. So,
and those get magnified by the blue shift.
Yes, that's in principle. Yeah, that's correct in principle.
Because Nick and I just finished a very similar calculation in microstate geometries. So
right. Yeah, we haven't done that calculation. That's possible. That is possible.
I was thinking about that as I was going, and if that piece of plumbing is done very, very smoothly, like it's cylindrical, you might escape the tidal destruction. See, the point is it's not good enough just to analyze Riemann squared in this context. What you've got to do is you've got to put in the actual velocity vector and see what the actual tidal stress is. And typically a low multipole can get a huge magnification, which then destroys or excites the stringy modes or whatever's going through. But it does depend a bit on the details on the bottom there.
Yeah. So maybe you say it's maybe more important that it's not capped, but it's actually just continuing through.
Yeah, I was worried exactly about that point.
Yeah, that is quite different from being capped, right?
If you make a nice cylindrical junction so it looks really flat, you might get away with it.
Okay.
Well, here it looks like empty ADS2, right? That's
yeah. I mean, in microstate geometries, it looks like BTZ, which is constant curvature, connecting to a global ADS3, and that can
also empty ADS2 actually.
Sorry.
It also looks like empty ADS2.
Yeah, but so
it's the same as Juan.
But there is a transition from this BTZ throat to a cap, and it's that multipole that kills you. And so, everything's ADS. Everything in sight in these geometries is sort of some kind of ADS2 in the microstate geometry, and still the transition zone is what just tidally excites you very, very strongly.
Yeah, but the thing is, it starts affecting you like way far up the throat.
Indeed.
So you have to make the multipoles very, very tiny in order not to have an effect.
Yeah, this ratio is related to the ratio between RE and the distance, right?
Yep. It's exactly just like in microstate geometries. It's related to the A parameter and the B parameter, and there's a redshift factor combined with a sort of geometric.
Yeah, exactly. But the point is that the redshift factor here is related to RE over L, right? Mm-hmm. But that's the same factor that will suppress the decay of the modes as you goes in, right? So I think that my feeling is that the magnification could make the forces here comparable to, at most comparable to the, well, just to the curvature scales that we have in the problem. Yeah. I mean, just the curvature 1 over RE squared. Well, I don't know. I haven't thought about it, so
it's not a hard calculation just to get a ballpark.
Yeah, I agree. It's easy. Yeah. So, yeah. I think that the same effect that enhances it, it also suppresses the perturbations as you go in. So I think it's likely not to matter. Well, I have to do the calculation. Okay, so so that finished the discussion of this type of solutions. There is an interesting quantum interpretation of this when you interpret black holes as quantum systems. So normally we like to interpret black holes as seen from the outside as a quantum system with e to the s degrees of freedom and so on. And in that case, the connected geometries are entangled quantum systems, and the proximity between these two black holes induce small interactions between these quantum systems. These are somewhat analogous to atoms that are interacting through exchange of photons that give rise to the van der Waals force, for example, and entangles the two atoms. So here, something similar happens when these fermions get exchanged between the two black holes. And the idea is that going through the wormhole is somewhat similar to being teleported. So one way of thinking of what happens is that you enter one black hole, you get destroyed and mixed into the degrees of freedom of the quantum system. And then your information is transferred to the other black hole by these fermions, the interactions mediated by these fermions. And then you are rebuilt on the other black hole. So that's, now this fact that any information that you send through the wormhole should be interpretable as being sent through the outside implies something. It implies that there should be some kind of bound on the number of qubits that you send through this process. And in fact, the number of qubits that you can send is bounded by this binding energy. Remember that we discussed the binding energy, which was 1/RE. So the smallest, so if we want to send the maximum amount of qubits, we like to encode them into modes that have very long wavelength. And so let's say we want to send them all in some time of order L, which is the time that it takes to travel between the two in the outside. So in that case, the best we could do is divide all our qubits into modes of length 1/L, and then we get this this distance. And then this will go like number of qubits over L. So that's the maximal information we can send in before the wormhole gets destroyed. And we said the binding energy was C/L, and C was the two-dimensional effective number of 2D modes. And so C is also the amount of information we can travel through, that we can send through the outside. So this formula is saying that the amount of information we can send through the inside is less or equal than the amount of information we can send through the outside with these modes. Okay, it's some kind of a consistency condition for this type of interpretation. So we discussed some conclusions. So we discussed some traversable wormhole constructions in 4D. They require some special matter consistent with relativity, but no exotic matter. This matter is present in the standard model at short distances, and similar matter can be present in previously considered extensions like the Randall-Sum 2 model. I don't personally think that these extensions are likely to be realized in nature, or even if they were realized, that these wormholes would form naturally. But the solutions are found in what they teach us about what's compatible with the general principles of relativity and quantum field theory. They also have an interesting interpretation in terms of entangled black holes. Okay, thank you.
So thank you very much. So are there any more questions? Anybody?
Can I ask a question?
Go ahead.
If we consider the wormhole as you described it in the Randall-Sundrum model, what type of boundary conditions I would need to put to solve and find, in principle, the solution?
Yeah, so in 4 dimensions, yeah, so for the metric, you put the boundary conditions of the 4-dimensional metric ansatz that we discussed. So in R4 space with two extremal black holes, and then join at the bottom through with ADS2. So that's the boundary condition for the metric. And for the gauge field, also the boundary condition is the same as what we have in the 4D construction, 4D metric. Is that clear?
Yes, but is this enough? Is that covering the fact that you have a dynamical zero mode on the brain for the gravity?
Yeah, yeah. So that we know that in Randall syndrome the dynamical zero mode gets an equation of motion, right, which reduces to the 4D gravity equation of motion.
I see. So you're saying that once this satisfies the 4-dimensional equation, this is okay.
Yeah, yeah. We expect that plus some corrections. I perhaps should emphasize one thing. So when you have this matter, you will also get some other corrections that I haven't explicitly discussed that are compatible with the ADS2 times S2 isometries. So there are all those corrections, but they those corrections, all they do is just change slightly the radius of the S2 or the radius of ADS2, but they don't make the wormhole either less or more traversable. So we focused in the discussion, we focused on the leading correction that violates the symmetries of ADS2.
Okay. Roberto Emparan has a question. Go ahead.
Yeah, sorry. Hi. So you saw the slide where you have an ADS2 surface inside ADS3, right? Which is
yes,
so this ADS2, that's not geodesic surface. It's not a minimal surface over there, right? Because usually if you have an ADS2 slicing of ADS3, it would be
this one here. Yeah.
Yeah, that's right.
Yes, yeah, indeed.
So this is because the pressure, or you have some tension or some pressure on the, or some effect on the, on this, well, what we might call the ADS2 brain.
Yes. Yeah, that's right. So, well, it has to join to the 4D geometry, right?
Yes.
So that, if you wish, exerts a pressure. But one other way to understand why it's not a geodesic surface is that the extrinsic curvature of this surface is related to the stress tensor, right? The second fundamental form. So that the curvature tensor, no, not the trace, but even the tensor itself.
And this is also, yeah, okay. Well,
yes.
Yeah.
So the fact that it has a non-zero stress tensor, it's related to the fact that this this is not a geodesic surface.
Yeah. And this is also a reason that this ADS2 part has to be longer than the purple part that you have, right? Because otherwise...
Yeah, that's right. Yeah, if you, yeah, actually, if you start separating D from the, so if you start making D larger, right?
Yes.
The equations change slightly, but what starts happening is that as you make D larger, the distance L that we were talking about becomes larger, okay? So both become larger. And these two surfaces that we have here, they become more equal in size, and they also become closer to geodesic surfaces.
Okay. But you cannot...
surfaces you are used to in just the ADS2 slicing of ADS3. And also the stress tensor inside this throat becomes smaller and smaller, and the throat becomes longer and longer.
Okay, thank you.
Yeah, sure.
There's a question from Giuseppe. You have to unmute yourself, Giuseppe.
Oh, okay, yeah. Can you hear me?
Yep.
Yes.
Yes. So you say that if you bring two black holes close together, you expect that this wormhole might form by tunneling, right?
Yeah.
And
I didn't say the time scale. There might be some. Well,
you say that it would take exponentially long time or something.
It might take exponentially long time. I don't really know what the time scale
Doesn't need to, right? Because the throats are very long. And because the throats are very long, the energy to connect is very, very weak because it's very, very redshifted. So, you know, the tunneling can actually be quite large because, you know, the throats, I mean.
Yeah, I don't know. Yeah, so I think there are some arguments that, well, let me just, since you made an argument that is short that I kind of like, let me make an argument that time scale is long. So
okay.
So if you have two near extremal black holes, they have some extremal entropy, right? And that entropy needs to be radiated away before they can reconnect. And if the temperature is low, it would take a long time to radiate.
Yeah,
that
but this entropy again, if you assume that they're a pure state, and if you have, for example, two throats which are like just long, and you just look at a pure state and another pure state.
Well, I guess the question is if you can make this through some physical process, right? You would imagine that the physical process might involve forming two separate magnetic black holes and then bringing them close together so that they interact with each other and then select, maybe they would decay into this wormhole. This is the process I had in mind here. Maybe you come up with a different process that didn't involve making a black hole in the first place at all.
No, I mean, for example, if you take a long throat, I mean, with whatever, I mean, you can end it with a cap if you want, and you take another one, and then you ask, what's the probability of the caps to join? It's very small because, the energy which it costs you is tiny.
Right.
So I think that's...
Okay, that goes into the direction of saying that it will take a long time.
No, short one. So the throats are huge, and then the energy at the bottom is tiny by looking at the UV. Yeah. So then they can connect with each other. It doesn't cost too much energy. The hill over which they have to jump is very, very small because of the redshift. So the tunneling will be happening very quickly. It's a bit like like a shell tunneling into fastballs. The same thing. I mean, because the redshift is very large, all the hills become very small. So then the tunneling happens very fast.
Okay. Well, I'm not sure I understood the argument, but
I think the throat being long again. If you look at how much energy they have to tunnel over in order to go on the other, in order to merge the two throats, the energy being at the bottom of two very long throats is very, very small.
Well, but it would seem that the rate would involve some proper size of some action of some path that is defined in the infrared, right? And that path that is defined in the infrared will have an action which is of order the extremal entropy. I mean, it's an action of order RE squared.
Because the thickness of the throat is the extremal entropy. Okay, fair enough.
But yeah, I mean, it's a reconfiguration of the geometry at the bottom near this region, and it's a naive estimate would be that one, the black hole entropy. So
yeah, my question was actually if it is compatible with bounds on the time it takes for two systems to get entangled, for two quantum systems.
Well, I guess I'm not. What bound are you thinking about? This is.
Well, I don't have a precise bound in mind, but there should be, I guess, some statements about how long does it take for two systems to get entangled.
Yeah. So. Yeah, in this context, it's not only that they should get entangled, but they should find this particular entangled state we're talking about that minimizes the energy, right? Among all possible entangled states, this is just one, and the question is how easy it is to find it, or to guide, how easy it is to guide the system from a generic state to this particular state.
Okay, thanks.
Any more questions? Anybody?
Actually, I had a question for Juan. So actually, I can ask a similar question about this timing. If you look at a bubbling geometry, which has a huge bubble, and you ask, which again has the same size as the throat thickness, and you ask what's the tunneling probability of this huge bubble into two bubbles which are half the size. That's a big configuration. That's a configuration of things which have the same scale as the thickness of the throat of the black hole.
Yes, yes, yes.
And I think that number is small. And using a similar argument, one can show that, if you have your configuration, which has, again, two throats next to each other, the chance of them merging is, again, something which happens, they're big objects, but, they're very, very highly redshifted. So I think that should become small.
Well, it's not clear in what sense they are next to each other. I mean, in this 5-dimensional picture, it looks, at least in some ways of thinking about it, that they're close. But they are not, when you extend
Yeah, no, that's a fair point.
Yeah, and but even the first statement you said, I'm a bit surprised. So
Yeah, this is something which we did with Andrea Pum and Daniel Meyerson and Bert. It's about tunneling into bubbles.
Okay.
The numbers are very small. Again, if you look at the redshift, I mean, the tunneling is almost of the order e to the minus s. So, and that's happening because the redshift is very large. And essentially all the hills you have to tunnel under become very, very shallow.
So the tunneling rate is e to the minus s?
Yes, if you look, for example, M2 branes, which are merging and then, tunneling into a bubbling geometry.
Right, but that was the estimate that I would naively guess, right? E to the minus the entropy for the tunneling rate.
But what's happening there is that you're changing into, you're going from one big configuration, like let's say 3 bubbles into something which has 4 bubbles. So that's a huge difference of topology and everything at the bottom of the solution, and that doesn't cost you too much energy again.
Yeah, but I think the energy is not necessarily what's relevant, but it's the action of the instanton, right? And
yes. So there it was e to the minus s. We calculated it in this that example. So
yes. So that that would be my naive estimate, but that would lead to if that was the estimate in this case, it would lead to an exponentially long time scale for the black hole to form, for the wormhole to form.
Oh, I see. That's a fair point.
Small rate means. Yeah.
Oh, okay. I see, because it's only one configuration. Okay, fair enough.
Right.
Okay, very good. Any other questions? If not, we can thank Juan again. Thank you very much for joining us today.
Sure, yeah. Thanks for the invitation and best wishes to everybody.
Yes, best wishes to you, and let's hope to see you in person next time.
Okay, great. See you.
Thank you. Bye.
Bye-bye.
Bye.
Bye, everybody.